The next speaker is Jean-Philippe Airiau. After a master's degree in computer science, he divided in the world of modeling and simulation tools applied to French Navy fighters. He started working for CEA in 2004 as a project manager of the CEA laser software Miro. Now he is in charge of other operating tools for the laser Megajoule facility like PARC. Jean-Philippe will give a talk on PARC, a computational system in support of laser Megajoule facility operations.
Thank you for the introduction. Good morning. So I'm Jean-Philippe Airiau, work at the CEA on the laser Megajoule facility. I'm a technical manager of PARC. PARC is the French acronym for Automatic Bundle Settings Prediction. The first idea of using an automatic tools for predictions in the laser Megajoule facility was first mentioned in 2004. The specification job was started in 2013, and the first release of PARC has been deployed on the facility in August 2014 for the first experiment. And now we are running the third release of PARC on the system. And to understand the system, I have to explain the context. So for the laser Megajoule, the CEA faced a big challenge in order to meet the specifications of an automatic predictive and reported system. Such a systems manage multiple fields of applications, so laser, synchronization, alignment, deal with heterogeneous data coming from the control command system. You have to gather and run a lot of heterogeneous micro software coming from the previous feedback and the previous facilities. And you have to integrate EV laser simulation software like Miro. And finally run thousands of computations in a few minutes, because we are going to have 176 beams on the facility. So PARC solves this challenge and enhances the overall process. And now, just to understand how PARC has been designed, I will talk about the environment. The environment software architecture often reflects the facility design. For the LMG, it's logical for the low level of control command, like embedded software and equipment, but it's not so trivial for the upper level. PARC is seen in the system as at the level of the application, at the level of applications. We have the shot management at the same level. It calls PARC during the shot sequence. PARC mimics the LMG design. I mean, we have here the facility. We have multiple laser bays depending on the geographical position and the target chamber in the middle. Each bay contains bundles up to 6, and each bundle has 2 quads, and a quad at 4 beams. And PARC's design mimics this architecture. So this brings me to the first main feature of PARC. PARC needs to exchange data with the control command systems. The most important thing here is to produce, for computation, homogeneous data, because we have a lot of data coming from the command control system with different field of application, so different types, different units. So it is important to run computation with homogeneous data. Source producer and target consumer are identified in a dictionary as templates. We've seen the IDs here. Those templates are instantiated depending on the perimeter of the experiments, I mean the number of bundle, quad, and beams. Here's a sample example of how we exchange data with the control command system. So PARC needs to get the scope frequency of the preamplifier module mounted on the upper quad of bundle 2. So PARC gets the corresponding IDs in the dictionary, instantiates templates for bundle 2 upper quad, and build a request, then send this request to the CCS DB API. The API answer with a pass to an HDF5 file, and then we use the secondary ID to get the parameter. So we have here an integer with a unit sample per second, and seems to be true. The validity status seems to be true. So PARC converts this data into its format with the information from the dictionary. So it will convert the integer in double, the units from sample per second to hertz, and then we instantiate the corresponding ID in PARC, and then create an XML file and write it in the PARC local database. So as we have all the needed data stored in our database in a homogeneous format, we can use it for computation. So all the microsoftware coming from the previous facilities or specifically developed for the LMG are described as computation module. A computation module is a short source file. The native language is Python, but we can use IDL or C++. It is designed to perform a specific feature. It can be simple or complex feature. We are trying to ensure generic design to ensure reusability. And the important thing that, we use the same mapping between memory structure and storage file format. All the files stored in the local PARC database have the same format. It's XML file, and it's described as a tree. It's mapped the memory, and you can see here in the file, once you load the file, you can access then the parameter from the memory input object. So you browse the level, the selected level, and the selected parameter to reach the data. Once you have this data, you can run the computations and then write this new parameter in a new XML file, output XML file. Not that you can, you have two ways to pass memory objects from a computation module to another. You can pass this memory object directly, or you can dump the memory object into a JSON file. This will be useful to understand the incoming slide. So finally, to describe this computation module, we have another associated file, an XML file with meta information. And in order to display the results or parameterize these computation modules, we need GUI windows. So we even go as far as designing GUI module. So GUI module, it's the same idea as computation module. I mean, we have a generic Python source file associated to a description file. But as we are using HTML page to display our result or parameterize our computation module, we need some more information for the GUI module. So in addition to the computation module, a GUI module have a definition file and one or more template layout HTML file. On the other side, PARC has a toolbox with all the elementary HTML model. I mean, how you display a string, a scalar, a curve, or an image. And what does the generic Python module do for this GUI module? It loads the definition files with all the links between the parameter in the database and the GUI parameter. Then you get the list from this definition file of all elementary HTML model we're going to use. You build these models with the real value, and then load the template layout files, and finally render the HTML page. So you have here the different kind of elementary HTML model we have, and this is a view of a short report using a complex layout and with the multiple elementary HTML we can use. So now we have computation modules, GUI modules. So we want to execute this module at a specific level of granularity. So this is the feature of the scenario feature. A scenario is just a simple XML file. It lists all the computation, all the modules, and the granularity of execution. As it is a simple XML file, we need to create the intermediate code between modules, and we want to be able to run multiple executions. Like at the beam level, we are going to run 176 computations. So we need to parallelize and distribute the computations. And to generate this intermediate code, we use a pseudo compiler. This pseudo compiler generates, depending on the granularity and the module, some multi-threaded script or distributed script. So this would be maybe clear in this slide, because this slide details how we use the multi-threading and the distribution. A multi-threading script, it's easy to understand what do a multi-threading script. It depends on the level of granularity. For example, if I use a full perimeter, full configuration experiment with a 22 bundle and 44 quad, we need 44 threads to execute the module at the quad level. And if we have some module to execute at the beam level, we are going to distribute the computation. So we use Slurm, workload manager. It's a common tool in the HPC universe. It can distribute our computation in a small cluster. And then we have a queue manager in order to avoid concurrent execution. This queue manager is performed by the Celery tool. And finally, this is the software configuration. So we have light clients for manual operations, communicates with the application server here by web services. The application server can be called by the control command system. It can execute scenarios, manage scenarios, and the scenarios are the computation server runs the computation of the scenario on multi-threading and distributing the computation on the cluster. And we have the wrapper exchange data with the control command system by web services. On hardware side, many of the LMG systems are virtualized, but for PARC we are using a physical hardware, physical architecture with a distributed storage system. It's GlusterFS with 1 terabyte per bundle, and a small cluster with 32 cores per blade per bundle. This slide is the last slide. How PARC is involved in the lifecycle facility. So we have many operations of PARC in the lifecycle facility: new bundle integration, campaign shot, experiment campaign, facility maintenance. And here are the conclusions. So PARC fulfills its roles of adaptive computational platform in support of LMG operation. We have many scenarios in productions, and we have identified many scenarios for the future. And we are working on a new project to gather all data produced by PARC to monitor the health of facility. And finally, I want to thank the team PARC. And thanks Ron Hars, Mike Shaw, Caitlin McCandless, Jean-Michel Di Nicola from Lawrence Livermore National Lab. We have a very effective collaboration with them. And finally, thanks the organizing committee, because such a collaboration couldn't be possible without this kind of event. Thank you.
We have time for just one short question, if any.